Okay, so let me quickly draw the diagram. So we have x, y, z coordinate system, and in this coordinate system we have this one is x, this one is y, and this one is z as defined in the diagram. And then we have a hemisphere, so it's like this at the origin, and then the shape is like this, so it's like called northern hemisphere. And then we have electric field with magnitude E naught, and its direction is z. So electric field is going in this direction, it's parallel to z-axis. And the question asks, what is the net flux through this hemisphere? Okay, so you have tried to solve it, so let me explain it, and then you can see how did you think about it. So there are two ways actually. One is mathematical, one is more of intuitive way. Mathematical ways are easier because you just get a mathematical answer, you won't have to think about it. But intuitive ways are better because sometimes they just teach you how to think, and so they're better. I'm gonna talk about both of them. So mathematical ways, so have you heard of area element? Right? So if you have this surface of the iPad, let's say this one, then you can define that this upper surface, upper side of the iPad, it has some area, and if we define the direction perpendicular to the surface, then this will be the direction of this area element. So this is our choice. If we define positive upward, then the other side will have a direction in the opposite direction. So what you do, you can also define, like you can divide this hemispherical bowl into small area elements, and then you can integrate all those small area elements to get the total area of this hemispherical bowl. Why I am talking about area? That's because if I have electric field and I want to calculate flux, then the formula is electric field dotted with dA. dA is small infinitesimal area element of the surface that is under consideration. Okay, and that's why I want to divide this surface into small area elements, because given the electric field, this is the formula to calculate the flux. There is another formula too, which is in terms of charge. So if you are given the charge, then you can use this formula. This charge is Q unclosed. This formula is only applicable on closed surfaces. Yes?
Do you have to specify the normal vector on the area element?
Yes, yes, we are going to specify it because it's very important. This is our choice, which direction we take positive of the area element. So we are gonna specify it. But the thing is, when I gave the example of that iPad, that was a plane surface. The area element was just perpendicular to it. Okay. This surface is not as a whole a plane surface. It's a spherical, it's curved surface. But if we make the small area elements, dAs, that I'm going to divide this surface into, let's say this is one small element of this surface, area element of this surface. So I can divide this entire surface into infinitely many small area elements, and then I can just add them to get the total area. So if I do that, the whole idea is that if we do that, each small area element is actually flat. Like on, for example, you know that the earth is as a whole spherical, right? We know that. But our room, the floor of the room is not spherical, because locally on smaller scales, these surfaces are plane. So for this area element, the direction of area would be something like this, let's say. Okay, so this is dA. I'm just going to take one area element, then I'm going to generalize it, like the entire surface is divided into a lot of area elements. But so this is the direction, and now you see the area is a vector quantity here, and this vector is not directed along any particular axis. And when this happens, we divide that vector quantity into its components. Okay, I'm just going to show two components. The y component will be in this direction, so this will be dAy along y-axis. Similarly, the small area element along z-axis will be this one. What about x? Since it's the third axis, and third axis is in this case coming out of the plane of the board, so the third dAx would be out of the plane of the board. Let's forget about x for a moment and just look at this one. Okay, so you can write this area element in vector form as dA total equals dAx x unit vector plus dAy y unit vector plus dAz z unit vector, right? Since it's a vector quantity and we are dealing with 3 dimensions, so this will be the small area element into its components. That's it. Here you can actually solve the problem. Okay, this is the mathematical way. So I can dot that with electric field, and if I do that, you see that electric field is given as E naught, which is the magnitude, which means electric field is constant in this region. This is very important, because when you know that electric field is constant, this is just a number, you can take it out of the integral. This is something very important, which is going to be very important when you actually study the Gauss's law. This is like the whole trick in Gauss's law. Gauss's law, like whenever you take symmetry, you assume that through the Gaussian surface electric field, like on the Gaussian surface electric field has the same value at each point. This is like the heart of Gauss's law, like when you apply it. So you can take this thing out of the integral, but first write the direction, which is along z-axis, and now it's dotted with this thing, which is dAx x unit vector plus dAy y unit vector plus dAz z unit vector. Okay, only one term. These are 3 terms because we have addition in between them. This multiplies with this term, this one, this becomes first term, then this dotted with the second, then dotted with the third. So we have 3 different integrals, but 2 of them are 0. Can you see which 2 are 0? X and y. You are taking dot product. So this is a number. This is now a number. So you just pull the numbers out. What are vectors here? Z and X, these unit vectors. Okay. So you are dotting Z with X unit vector. And this is the direction of these unit vectors. These are the directions. So X and Z. And these are just the axes, and we know that the axes are perpendicular to each other, which means they have an angle of 90 degrees. So you expand, I'm just going to do the first one. So you expand z unit vector dot say x unit vector. That gives you, unit vectors by definition have magnitude, unit magnitude, right? That's why they are called unit vector. So this will be 1 magnitude of z unit vector multiplied by 1 magnitude of x unit vector into cosine of angle between them. And we can see from this diagram that the angle between them is 90 degree and cosine 90 is 0. So this is 0. By similar argument, the second term goes to 0, z dot y will be 0. But then z unit vector dotted with z unit vector, they are in the same direction. Parallel angle would be 0 and cosine 0 is 1. Okay, so 1 multiplied by 1 multiplied by 1 will give us 1 and only, as you said, this term survives. Okay, so we will have integral E naught into dA. E naught is constant, dAz. E naught is constant, take this out of the integral and we have dAz. Okay, this was one small area element. Okay, we are gonna divide this entire surface into infinitely many area elements, and by the same argument exact this thing happens for all of them. And so you see that when we add all the small area elements which are pointing along z-axis, they just add up to make the total area along the z-axis. Okay, so this is the area through which electric field with magnitude E naught is passing. Yes.
Could you, so you said that the differential A is a vector quantity. Could you just decompose that and like have dA just as scalar values and just have the normal vector there that you just dotted with z instead? Does that make sense?
But normal vector is going to have some direction. This is the direction for normal vector. So if you write it dA, you can write it like this.
Yeah.
Yeah. So that's the same thing. Sometimes they use normal vector, just putting a line over A is easier, a vector quantity. Yeah, yeah. That's the same thing. Okay. So this is the total area through which electric field is passing along the z-axis. Now you look at this diagram and tell me what is the total area through which electric field is passing. So we are not considering the bottom surface. We are just considering this hemispherical bowl. Okay. But if you look at this, it starts at this point, ends at this point. So the electric field is going through this bottom region. So actually the area that we need to consider is just the area of the bottom region, because this is our bowl, although it's curved, but this is the maximum area that it can have. And the area of this bottom surface is pi r square. So your electric field becomes E naught times pi r square, where r is the radius of, let's say this is the radius of this bottom surface of this hemispherical bowl. That's the mathematical answer. Okay. You could have arrived at the same answer by arguing, just arguing intuitively. How do we argue that? So we took this one small area element, right? You could have taken a exact same size area element on the other side of this bowl. For this one, the direction of area element would be this one. Okay. And then you resolve it into components. This becomes dAy, this becomes dAz, right? And now you immediately see that this dAy is pointing along a negative y-axis. This is along a positive y-axis, and they are equal in magnitude. So they just go away. So you can extend this argument that when we divide this area into small area elements, there will be an area element. For every area element that is here, there will be an area element here, which cancels its y component. And for every area element here, there will be an area element at the back side of the bowl that cancels its x component. And you will see that all the z components, they will be non-zero. And you will immediately like skip this step, and you will arrive at here that the total area should be pointing along a z-axis, and the integration should be on the small area elements, which makes the total area of the z-axis. Okay. And so immediately you arrive at your result as like E naught into pi r square. And that's why I was saying that you can just look at the statement and write down the answer. But I want you to think about this thing, like how actually you make sense of that answer. Okay, the next one is interesting. The next one is if we rotate this bowl by 90 degrees, okay, around x-axis, what will be the total flux? So I'm going to redraw it again, but this time it's rotated by 90 degrees. So this is the situation now, x, y, z. And if I rotate it, let's say I rotate it clockwise, then the bowl will sit here, at somewhere here. Electric field is still along the z-axis. So this is E along the z-axis, and this is z-axis, y-axis, x-axis. Now what is the electric field through this bowl? Yes. Why? It's parallel to what?
The area. There's as much going in as going out.
That is a correct argument. That's from flux. You need to back up your claim.
Wouldn't it be because the dot product of, because it's parallel to the curved surface, no? After it's been rotated?
Let's okay, yeah. So no, let's talk about this expression. In terms of this expression, which component of area element will survive now? Like I divide this entire surface again into smaller area elements, as I have shown the y component of the area element, z component of the area element, x component coming out of the plane of the board. Which one? So here we saw that the z component survived of the area element. What do you think, which component will survive in that case? Should I also make two small area elements. Let's say this one going this direction. So this is dAy. This one is dAz. Okay. Take another one here going in this direction. dAy, dAz. X for both of these patches is coming out of the plane of the board. But then you can take two other small area elements at the other side of the bowl, which is into the plane of the board, and you can also divide that into components, and you will see that for those 2 points, X components will be going into the plane of the board. So we can argue that X components also cancels. Z components are clearly canceling here. Which one is adding up to give us the total area? Which components are not cancelling here? Y component. Okay, so this one survives. In that case, this one survives. But then you dot Z with Y and you get nothing, 0. That's the reason behind your answer. Yours were correct right away. You can just like, okay, electric flux is the number of lines passing through an area element. So if you see here, divide this into two parts. So we have some electric field lines going into the bowl, and then the same electric field lines are going out of the bowl. So net flux is 0. That actually comes from this argument too. We don't have any electrical charge inside that. Yes?
So if you were to cut it in half, like everything below the XY, so all you have is just above that, then it wouldn't be 0.
Of course not.
Right.
Then it would be pi r square divided by 2 times E naught.
Right.
Yeah. You see, this is very interesting thing. Like you can come up with all sort of these kind of things and think about them. Okay, so this was the problem that Professor Hammerling gave me, but I want to put one more for you, and that is even interesting than this one. So this is problem 2.10 in Griffiths' book. Yes?
I want to ask, so would it, for that problem that you just erased, it would have been E naught dAy?
Oh, it would be E naught Z dotted with dAy y unit vector. So Z dot y is 0. That's why it's 0. Yeah, because the electric field and area element, non-zero area elements are perpendicular to each other. This one that I'm going to write, this is problem 2.9 in Griffiths' book, but very interesting. You're going to see problems like this everywhere. So we have a cube. Okay, we have this cube. Damn, I'm very bad at making cubes. My drawing sucks. Anyway, so let's put this thing. Yeah. Let's put this thing at the origin of coordinate system. So X component is coming, X-axis is coming out, Y-axis towards right, and Z-axis upward. And now let's put a charge at the origin. Where do you want to put it? Let's put it here. That's better. Okay, you want to calculate the flux through any one surface of this cube because of this charge. Let's say you want to calculate the flux through this surface. How do you calculate it?
Take the normal unit vector. This is the first thing I would do.
The mathematics is very hard for this problem. Very, very hard. No one will recommend you solving it mathematically. And you cannot use this part because we don't have electric field. We are given charge. So think about this formula. Yes? You had a question?
No.
Okay.
And it's typical, right? Because you have to do it for 6 different times, right?
Yes. Can you think of an easier way? Just be innovative.
Take the area of one side.
We can. We actually are going to do that, but we need to assume something, first to make sure that we just get charge by using the flux by using this formula. So what you do, I'm just going to try and explain it. So this charge is at one corner of this cube. It's not entirely inside this cube, and
So you just add another box?
yes, not one.
Surrounding?
Yeah, but not one box. There are going to be many boxes.
Yeah.
But I like it. That's actually the answer.
Oh,
So we are going to look at Q unclosed. This charge is not entirely enclosed inside this cube. So let's say we add, so can you tell me with how many other boxes are the other, but okay, yes, but so this charge, it has only 1/8 of its, let's say if it has volume charges, they are small particles, they don't have any size, but I'm just assuming, let's say this is a soccer ball or a tennis ball, okay, then only 1/8 of its volume is inside this cube. The rest is outside. So what you do, you add 7 other boxes. So you add 1 here, 1 at the bottom, 1 here, and then 4 in front of them. And once you do that, then this charge will exactly be at the center of that bigger box which you have just made by combining 8 smaller cubes. Okay. And then you can just use this formula. Now this charge is at the center of that bigger cube. Yes?
I thought the formula only stands if it's considered a point charge.
Yes, it is a point
But
charge.
we're considering it to be 1/8 inside of the box. So it's not
Oh, I just, that was a very bad example. That's why I said that these charges, these particles, they don't have any physical dimensions. I just tried to explain it to make sense of it. Like if a charge sits at one corner of a cube, it's not inside the cube, only some part of it is, like a tennis ball or a soccer ball.
It's not fully enclosed
No, it's not fully enclosed. And that's why we are adding 7 more boxes.
to enclose it.
Yeah. So if we add 7 more boxes, this will be inside that giant box and will be at the center of that box. If it is at the center of that bigger box, which we have made out of 8 boxes or cubes, then the flux, then each cube, the cube has 6 surfaces. Total flux through all the surfaces is this one. What will be the flux through one surface of that bigger cube? Total are 6, so this will be 1/6 Q divided by 6 epsilon naught. What we are looking at? Flux through one surface of a smaller cube. Okay? And the one side of the cube, the area of one side of the cube is how many times the area of this one side of this smaller cube? 1/4. 4 times. So the net flux through one of these sides will be 1/4 of Q divided by 6 epsilon naught. So your answer will be for this problem Q divided by 24 epsilon naught. And you see, you just argue by symmetry and knowing the Gauss's law. You don't have to do any math for that. If you actually try to do math, it's gonna be horrible. Yes. Now I leave something for you as my time runs out. What if this charge is inside, but it's at this point? It's not at its center. What will be the flux through any one surface? Can you use it to calculate?
The origin.
It is. Oh, you can shift the origin, but then it's gonna just make the older problem. We are looking at a different problem. Okay, if it sits inside, but it's close to one of the sides of the cube. Can we use this formula? Why?
Symmetrical.
Symmetry of what? Why do we require symmetry? That's gonna be interesting now. I'll give you a week to think about it. I mean, if you really like physics.
Well, like if does it matter we're assuming it's a positive charge or anything? Like if it's a positive charge, then the charge is going to go outwards? Like
Field lines are gonna go out, right?
So, since
Okay, you are in the right direction, so.
like because of its position,
Yes.
it's going to be
You see, field dependence is on position. It's inverse square law. Electric field goes as 1/r square. So there will be more field lines passing through the bottom surface compared to this surface. So the flux through each surface will be different, and you cannot come up with any symmetry argument to solve it. If you actually do, it's going to be a hell lot of difficult mathematics. I have never seen it in any book. But of course, problem is going to be solvable, but it's going to be way more difficult.
We'd have to overlap the squares with inside each square. Like you could add another 7 squares.
Not in that case when it sits here. Because still, even you add 7 more spheres, these cubes, and it becomes one giant cube. Still, this charge will be not equidistant from all the surfaces of that bigger cube, the problem will still be there. Since the distance is not same, field lines are different from each surface, and if field lines are different from each surface, the flux is different. That's the basic definition. Field lines passing through area is flux. But yeah, interesting things, right?